We've seen in the previous topic how we can multiply matrices together. In this topic, we're going to see how we can use matrices to examine transformations that we studied in GCSE, so things like rotations, enlargements, reflections, those sorts of things, how we can use matrices to represent those transformations. So here I've got a matrix A, B, C, D, and I'm multiplying, so this is a 2 by 2 matrix, and I'm using this to multiply another matrix or a column. This is obviously a column vector here, so quite a simple matrix. I'm using that to represent the coordinates x, y, and when I multiply the matrix A, B, C, D by the matrix x, y, I get another matrix, ax plus by and cx plus dy. So I get another column vector. This is a column vector just like this is. So I'm taking a coordinate xy, I'm multiplying it by this matrix, and I'm getting another coordinate, ax plus by and cx plus dy. This is the new x coordinate. This is the new y coordinate. So I could call this x dash here. So my new coordinate, my new x coordinate x dash, is given by a times the old x coordinate plus b times the old y coordinate. And my new y coordinates here, I'll call it y dash, is given by c times my old x coordinate plus d times my old y coordinate. So this A, B, C, D represents a transformation of this coordinate onto this new coordinate. I could call this transformation, I could just name it T, and that allows me to write this in a slightly different way, where I can say the transformation T to the coordinate xy gives me my new coordinate. So, for example, here I have a triangle, T, and a matrix, 3, 0, 0, 2, and I'm going to transform this triangle T, with this coordinate, with this matrix, sorry. So first of all, let's look at the coordinate here, the coordinate of this triangle, 0, 0. So this is the coordinate 0, 0 here. If I multiply the matrix 3, 0, 0, 2 by 0, 0, then I will obviously get just 0, 0. So the origin, the original 0, 0, gets transformed to be the new coordinate 0, 0. So actually this coordinate here doesn't change at all. The vertex here, the coordinate 2, 0, when I multiply that by the matrix 3, 0, 0, 2, I get 3 times 2 plus 0 times 0, which is 6, and 0 times 2 plus 2 times 0, which is 0. So this coordinate here, 2, 0, gets mapped to the new coordinate 6, 0. And then finally this coordinate here, that's the coordinate 0, 3. If I multiply that by the matrix, then I get 3 times 0 plus 0 times 3, 0 times 0 plus 2 times 3. So this coordinate gets mapped to the coordinate 0, 6. So I have my 3 new coordinates, which I can now plot on. So I've got my 0, 0 here, my 6, 0 here, and my 0, 6 here. And this is my new triangle. I call it T dash to represent the new triangle. We call this the image. The result of the transformation, we call that the image. And we can see here that basically what this matrix here represents is the transformation where the x coordinate has been stretched by a scale factor of 3. See how in the x direction this triangle has been stretched by a scale factor of 3 in the x direction, and it's been stretched by a scale factor of only 2 in the y direction. So you can see from this example how we can use matrices to represent more complicated transformations than we had previously dealt with at GCSE. At GCSE we dealt with enlargements, but we'd only ever dealt with enlargements where the scale factor was the same. Here we can see we've got a different scale factor in the x direction and the y direction. By the way, I did this calculation in 3 different goes. I could have represented it all in one go by just combining those 3 coordinates into one matrix like that, and then if I multiply this matrix, the transformation matrix, by the coordinate matrices, I get the image coordinate matrix there. Now, the title of this topic is linear transformations, because not all transformations are linear transformations, so we need to talk about that. The transformation T here of the coordinate x, y, this transformation T maps the coordinate x, y to be the coordinate x plus 2y and 3x. I want to find out what that matrix is. What is matrix T? I know this has to be a set of numbers here. So in this case here, I know it's going to be a 1 and a 2. Because I know I've got 1 times x plus 2 times y to give me x plus 2y. Just to repeat that, 1x plus 2y. Down here, I know this is going to have to be a 3 to give me a 3x, and this is going to have to be a 0 to give me a 0y. So 3x plus 0y. So the transformation T is the matrix 1, 2, 3, 0. This is a linear transformation because I can represent the transformation with a 2 by 2 matrix where each of the elements is a constant number. Next example. The transformation V maps the coordinates x, y to be the new coordinate minus 2y and 3x plus y. And again, I want to find the matrix that represents the transformation V. In this case, I know that this is going to have to be a 0 because I want it to be a 0 times x. And then I want it to be a minus 2 here to give a minus 2 times y. So 0x plus minus 2y. And on the bottom row here, I know this is going to have to be a 3, and that's going to have to be a 1 to get a 3x plus 1y. Again, this is a linear transformation because I can represent the transformation with a 2 by 2 matrix where each of the elements is a constant number. Now, here comes the one that is not a linear transformation. W is not a linear transformation. And I'll explain why. Because if I wanted to represent this with a matrix, there is no set of numbers here. There is not an A, B, C, D. There's not a 2 by 2 matrix here that I could use to represent the transformation that maps x, y onto x squared y plus 3. I can't multiply x by a number and get an x squared. The only way I could multiply x to get x squared is to times by x, not by a constant number. Similarly down here, there's no number that I can multiply the xy by that will give me a constant 3. So this transformation here, and it is a transformation, but it is not a linear transformation, so we can't represent it with a 2 by 2 matrix. In actual fact, if you think about what this bit here means, this is just taking the y coordinate and adding 3 to the y coordinate. So this is actually just simply a transformation, a translation of 3 in the y direction. So you might have noticed when I was talking in the introduction about going back to GCSE transformations, I talked about enlargements, I talked about rotations, and I talked about reflections, but I didn't say translations, because a translation is not a linear transformation. We can't use a matrix to represent it. Anyway, the point that I'm trying to make here is that a linear transformation has to be represented like this. It can't be, basically you have to have a 2 by 2 matrix where each one of the elements is a constant number. That's what a linear transformation is. So what you need to know is what a linear transformation is, like I just said, and to be able to perform a linear transformation, like in this example here. I've got a square here, I've called it S, and I want to use the matrix -1, 2, 2, 1 to transform this square and see what happens to it. So first of all, I'm going to pick this first coordinate here, 1, 1, and if I multiply that by this matrix, I get -1 times 1 plus 2 times 1, which gives 2. Sorry, gives 1. And then 2 times 1 plus 1 times 1 is 3. So I'm saying that this coordinate here gets mapped to the new coordinates 1, 3. So in actual fact, that one will just get mapped to be up here. Next coordinate, I'm looking at this coordinate here now, which is 3, 1. If I multiply that by that matrix, I get -1, 7. So in actual fact, this coordinate gets mapped to -1, 7 over here somewhere. 1, 3, so that's this coordinate here, 1, 3. That gets mapped when I apply that matrix to this coordinate. I get the coordinate 5, 5. And then finally, the last coordinate, 3, 3. If I apply the matrix to that, I get that. So plotting all of these new coordinates, so I have the 1, 3 here, I have the -1, 7 here, I have the 5, 5 here, and the 3, 9 here. And so what we can see here is that not only has the shape S, the square S, been enlarged, it's also been rotated a little bit as well. So this matrix here represents a combination of different transformations. The precise details of those transformations are not important at this stage. We'll cover that in more detail in a later lesson. But the key thing that I just want you to take away from this is how we can use a matrix to represent transformations to coordinates, and how that can then represent transformations to shapes, and what a linear transformation is, how it has to be represented by a 2 by 2 matrix where each of the elements is a constant number.